So for this subject, I mean, to discuss these quantum correlations for light scattering in free space, we really going to see here just process that mostly of you are very familiar with. So it's important to have first a bit of a digression about this quantum to classical relation. And I mean, in quantum mechanics, I think quantum mechanics never stopped evolving, especially in this discussion about the concept about what is purely quantum or classical. And I think this is a work that is very famous about from Zurich, where he really introduced this important notion of decoherence as a way to understand the passage of this fuzzy quantum reality to the more concrete classical world. And this was already a big development with respect to the beginning of quantum mechanics, that we had this discussion about the role of the observer. So in this decoherence picture, you have just the universe. I mean, the quantum systems just interacting with the rest of the universe. It gets entangled, but it's too much entanglement. And then you end up losing this information, and you end up having this more concrete reality. But actually, this is also like a view that's already, I mean, we passed from that. I mean, this is from the 1980s and 1990s. I think nowadays, I mean, the focus, I think, is more that just no classical world. So we don't need to care much about this boundary, about having a macroscopic signal that should behave like a from classical physics. And actually, I mean, classical physics was never meant to explain everything. I mean, quantum mechanics explain much more. I mean, it's much more ambitious theory. And you end up always with these classical theories in a circular argument, in the sense that classical physics explains the part of the world that classical physics explains, basically, because there are many parts of the world that has no relation with classical physics. And the other point that's very different is that decoherence just means that the system is not isolated. And now we love this non-isolated or quantum entangled system. I think that's also a change. And the third change in view, I would say, is that decoherence is opportunity, in the sense that you have transduction. So decoherence means that you are passing your quantum properties from one system to the other, and you can use that to do many different things. And this is the origin of many different fields that are popping up today. So we have, for example, optomechanics. So we use the vibrations of mirrors and other objects that connects with light. And of course, it's a source of decoherence, but also you are interacting an optical field with a mechanical motion, and then you can use that. If you do the calculation from first principles, you have interesting physics coming from that. But you have a whole bunch of new phenomena like cavity optomechanics, cavity electromechanics, and many different new fields that are all related with these interactions of your physical systems with the environment, that once you understand, you start to use that. Okay. And actually, what we are going to discuss here is the oldest and most well-studied example, which is spontaneous emission. Okay? So spontaneous emission is a decoherence process that was, I mean, it was explained a long time ago. So that's what I call the oldest. And when I talk about spontaneous emission, what we are discussing is just light, the light that we see, basically. So it's ubiquitous. And just to recall a bit, I mean, it was first discussed in the connection with the Bohr atom, in the beginning of quantum mechanics, with respect to quantum jumps, and the name spontaneous came from that problem, because spontaneous means without a cause, okay? And later, I mean, even before having the cause for this emission, there was already important developments, like in Einstein, he really developed the concept of spontaneous emission with respect to recoil, not just energy, but also momentum. But the explanation came really with Dirac, with the development of quantum electrodynamics, and this was the first theory that derived this rate of spontaneous emission, and then explain that it comes from the interaction vacuum modes. So strictly speaking, after Dirac, you shouldn't call this spontaneous anymore, because actually we know that's just vacuum-induced emissions. But okay, the name stick, and it's kind of tricky, this name, because if you don't know the cause, then you should use, for example, some kind of master equation to really quantify your lack of knowledge. But actually, since we know the cause, then you can really model from first principles any problem with spontaneous emission. And up to today, I mean, you still have a lot of more models related with master equations with spontaneous emission that sometimes get rid of the quantum effects just right in the beginning. Okay, and so, but the most well-known form of this theory for the explanation of spontaneous emission came from Vaskov-Wigner in the 1930s. That's the final form that we use nowadays. And just to start with the Vaskov-Wigner theory, so what we have here is just we consider a two-level atom with the atom initially in the excited state, and these atoms interact with this quantum vacuum around, which is just a broad band, a broad bath of plane waves comes from all over directions, and at the ground state energy. And as a result of this interaction, so you end up going to the ground state, the atom. This is an irreversible exponential decay, and then we have the experimentally observed rates for this process. No? And this looks really good. It's an example that you can explain the coherence, no? Because this is an irreversible process, and then you end up in a very well-defined state. But for what we are going to discuss following, it's important to have in mind that this is not the whole story, because what happens at this final state is actually not exactly this state. This photon you can emit in a particular direction, and then the atom will suffer recoil in the other directions, or you can emit it in another direction, and so on, so on. And actually, this is a highly entangled state between atom and light. So at the most basic level, you end up having this really huge entangled state. And that's a problem for quantum mechanics. I mean, this makes the work for the physicists hard, but also makes the world interesting. So I think it's interesting that you have this complexity at the bottom, I would say, but it's important to have in mind that you have this to start with, all discussions. And actually, we just put in the archive, I mean, 2 days ago, a paper on this subject where we quantify the amount of entanglement in this kind of process. This is a slowly evolving problem, I would say, through the last 100 years. But because it's the problem of how you quantify this state between atom and the atom and the photon that's emitted. Actually, the way we quantify this problem is that we calculate the purity of a reduced state. Just to explain what this is, let's say that you have a bipartite pure system in an entangled state. In this case, we have an atom and a photon. And a way to quantify the entanglement in this system is to look just in one of the parties and ask how pure it is. So the more mixed the reduced state is, the more entangled the bipartite state. So I particularly like this measure of entanglement in this problem because we always have in mind that spontaneous emission, once you shine light in an atom that starts to spontaneously emit, it starts to heat up. Okay? So when the atom heats up, it gets in a more mixed state. So that's our measure of entanglement. Okay? Once the atom gets mixed, that means that the information is actually connecting to the rest of the universe. And actually, we end up developing some like a phase map. Not exactly a phase map, but we end up classifying some entanglement regions. It depends a lot of the atom and the atomic transition. So here you have this first three lines here, D2 lines of cesium, potassium, and lithium. These are these three lines here. And the last three lines are two narrow lines from potassium and lithium, these two. And the last one here is the strontium. And we have just these parameters, these recoil temperatures, the temperature related to the energy of recoil of an atom, or the Doppler temperature that comes from Doppler cooling. And this uncertain temperature is just that we are putting temperature, the units of the spread of the initial wave packet in momentum space. And with these parameters, you can actually reach this picture here, where you have these regions of different kinds of entanglement of the atom with the photon. And we have regions of low entanglement and regions of a high entanglement here. And this just to point out that, so you have already just one atom emitting a photon, you have already like an interesting picture. And particularly, you have a lot of resource, because I think more and more we understand quantum entanglement as a resource. And that's why we need to quantify it. Okay, okay, so now let's go, go ahead. Yeah. Okay, so recoil entanglement is in a situation where you are really, we are dominated by the problem of the direction that you emit is going to have is connected with the recoil direction. So it's like the picture that I just showed with the Weissel-Wigner state, the final state. That's the most intuitive way to see. Actually, the Doppler entanglement is when you have a lot of initial momentum spread, and then you're not going to be as sensitive to the recoil. But when you have a lot of spread in the momentum space, and then you emit a photon, and the photon is much narrower than the spread in the momentum space, you can detect, actually, you can squeeze the momentum space when you detect the frequency of the photon. Then it's like you know already, more or less, what's the initial energy. Yes. Yeah, that's, yes, modulus of the momentum, that's the recoil temperature, but this, you see the line, it depends also on the uncertainty on the photon energy. So it ends up being really quite different mechanisms in the end of the day. Historically, you find more work on Doppler entanglement, even though the recoil entanglement is much more intuitive, I would say. But we need to quantify that. Even when we go to the recoil entanglement, that it gets deeper and deeper into this regime. So even each of this kind of entanglement, it can happen with different intensities. So let's go to the next fundamental process. This is Rayleigh scattering. So what we are considering here is just laser excited ensemble of two-level atoms. So it was really nice to have the talks. Yesterday we have two talks on this kind of problem, which is different from spontaneous emissions. This is more like what's called resonance fluorescence. So you spontaneously emit, but you are being forced by a laser field. And what's different here is that in free space, in the ensemble, you have a lot of contributions from different atoms. So typically, you have competitions between photon pairs comes from different atoms, or photon pairs coming from one atom, for example. That's what dominates this kind of problem. But what we're discussing here is then, you're talking about elastic or near elastic scattering. That's the kind of problem that we have in mind. And this is an approximation of almost anything, any system that you are exciting with light close to a resonance. You can think in first order to approximate by a system like this, an ensemble of two-level atoms. And let's start then with this really more simple experiment. We're just exciting an ensemble of cold atoms in vacuum, and then we collect light with a particular direction. And then this goes to a Hamburg-Brown twist interferometer, as it was described yesterday by Arno and by Lucas. And in this interferometer, then we analyze the statistics of light. And to have pure two-level systems, what we do is that we excite with circular polarized light in a cycling transition of rubidium-87 atoms, and then we end up in this cycling transition here in the end of the MF structure. And what we see when we get the G2 function, so this G2 function is the correlation function that was well discussed yesterday. So it depends on how you measure the coincidence here in time t and time t plus tau. And then you see here nicely, it goes from 2 to 1, and that's what's expected from a thermal light source. So thermal here is more like thermal statistics, light source. I'll come back to this. And it was expected to have some bunching at 0 delay. We have this G2 equals 0, but when we have delay going to infinity, it should go to 1. So this is a classical, a standard model for classical physics here. You can find this adaptation of the model to the problem in this article, but actually you can find this general discussion here in Loudon's book. And if you, in this problem, what you have is that you can worry, this source can be understood as a chaotic light source, chaotic in the very old sense of quantum optics that was not very popular later, but in the sense that you have the different emitters, they don't have any phase relations between them. But the output in the detector depends on the sum of all electric field from each of the emitters, and the emitters have just a single frequency, but they have a stochastic phase. But then when you calculate the G2, you end up with 1 plus the sum of the correlation functions of the phase of each emitter with itself. And so for this particular system, what leads to this phase variation on first order is that the light is absorbed in one direction, then emitted in the other. This gives a phase difference. And the light comes from a particular point in space, that's where the atom is located. And then the atom is moving from this location with a velocity VI, and this velocity depends from atom to atom. So this cold ensemble still has some temperature. Okay? And then when we see the difference in, you see that this correlation function needs the difference between the phase in different times, and you end up, this difference just depends on the velocity of the atom. And then when you take this account in these correlation functions, you end up with this G2 that goes exactly like this. And you see that at tau equals 0, you have 2, tau going to infinity, this goes to 1, as expected. So this is a standard treatment. But actually, you can do the same calculation using quantum theory. Okay, so you have the same problem, but now you have your internal structure of the atom. So you have an excited state. You have some, the excited state has some momentum. So you have the ground state with the same momentum. So you have internal and external degrees of freedom. You have some detuning from your resonance. And when you have the detuning that's much larger than the natural line width, you can adiabatically eliminate this excited state. If you consider null magnetic fields, so you have degenerate energy levels here in the ground state, you see that the initial state is like this. I mean, each atom has a different momentum, and you have some coherent state that's exciting the system. You have the vacuum modes that are initially non-populated. But then, after the first detection, what you have is that one atom received a kick, okay? But you don't know which atom is, okay? So you end up with an entangled collective state momentum space. And this is a general thing. Every time that you try to do a quantum theory from first principles in this kind of ensemble, you end up with collective entangled states. And once you see what happens after the second detection is that each atom evolves with a different phase. And once you take this into account, you end up in this exactly the same formula as the usual classical model. Okay? And you end up with the same kind of behavior. But this is just to point out that if the classical theory works very well, it doesn't mean that you don't have a quantum theory that's kind of different behind it. And most of the quantum effects that I'm going to discuss, they are going to be mapped in this kind of states. Sometimes these kind of states will lead to the same result of a classical theory. Sometimes they won't. Okay. So, let's go back just to one point. So here, I don't see any particular quantum trace. So we have a classical explanation for this kind of curve, but why we don't see anything that's more quantum, let's say? And from a quantum information perspective, the problem is, where is the information? Okay. So when we are detecting here in this Hamburg-Brown twist interferometer, you're detecting the properties of the light. But clearly, the atom got some kick in momentum when it emits light in this direction. And so when you detect in this direction the light, you left some information here in the atomic ensemble. So what we can do to retrieve this information is we can just move the process back in time. So we can do this in some situations and through an experiment configuration called four-wave mixing. Okay. So we can, what we do here is that we do the same process that we had before, but now we come with a second exciting laser in the opposite direction. And this second exciting laser actually retrieves the information that was in atomic system in a second light field. And by doing that, it leaves the atomic state in the same state it was before. So this is called a parametric process. So in nonlinear optics, these are responsible for the nonlinear signals. Is when you have this parametric process, and then you have conservation of energy and momentum all in the light fields, and nothing's left in the atomic system. So we do that to try to access more quantum process in our system. And when we do that, then of course we are going to start to see, as Arno mentioned yesterday, you end up to have competition between these different ways to come back to the initial state. First of all, for this pre-Rayleigh scattering, you have two photons absorbed by one of the two of these exciting fields, and two photons emitted. And here you have some sidebands. Now we have different meanings for this process, because this sideband, this is a process that only occurs at single atoms. Okay. But this one, you can have one photon scattering from one atom and the other scattering from the other atom. Okay? So this is a challenge for ensemble measurements, because you are competing with contribution from different atoms, which means that this process grows with n squared, so it's the number of atoms squared. And what happens is that you need a process like a parametric process. For this to dominate, this need to be n squared as well. And that's where the parametric process enters in place. But when we're doing, we have two modes, we have correlation between two modes, we need a different Cauchy-Schwarz inequality that Arnold didn't get to that yesterday. He was talking more about autocorrelations, correlations when you measure in a single mode. But when you have two modes, actually you have to use a different relation. So you have this G12 is a cross correlation, it's the same function, but you have the intensity of a detector in one photon with the detector in the other photon. So you have this cross correlation square divided by the autocorrelations for one field and the other. And once this is smaller than 1, then you can explain this with classical correlations, but once R gets larger than 1, then it's really quantum. And what we expect here, we already saw that the autocorrelations are going to be around 2. That was the previous experiment that I described. But then when you have this cross correlation above 2, that's typical indication that you are in this quantum region. And that's what we get from this experiment. So you see these oscillations in cross correlation that are really analogous to what was discussed yesterday with Arno. So this is this interference between the Rayleigh scattering and the sidebands. And we have this cross correlations above 2 here, and this autocorrelations going up to 2 in 0 on top. And then we have this number here for R that's around 2, and so we violate this classical bound. Here is the this is the plot of the R itself. And as Arno explained yesterday, so we can really understand well this process in this picture introduced by Dalibard and Serge Renaud, I mean, in the end of the 70s, beginning of the 80s. And so actually there was different attempts historically. So this is a very basic signal. And so it was tried to be observed in the 80s in this French group, and also in the 2000s in the group of Chengguan Du. But actually, so it's a group in Stanford and Maryland. They developed a theory for that, but they were not able to observe. There is a detail here. This G2 around a little bit below 3 and this R around 2, these are actually small numbers, okay? Because we have classical bounds here, but we don't have quantum bounds. So when you're talking about, for example, parametric down conversion or the Raman process I'm going to discuss soon, I mean, the G12 can go to hundreds, and the R can go to thousands or tens of thousands. So this is really just it's clear a violation, but it's a small violation. So basically anything you can lose that. And I'm telling this story, I mean, backward in time. So we started in our group working in Raman transitions, and then actually we took care of the system as looking for, as optimize this kind of quantum correlations for Raman transitions, and that's why we could observe these correlations for two-level transitions, because they are small, but if we take care of this collective state well, you can still observe it. So just to give an idea, where's the collective state here? The collective state is, as Arnold mentioned yesterday, in this process, we have two photon emissions. One comes from this 3-photon process that you end up in the excited state. So most likely what we have here is just a collective state in the excited state, and then this state goes down eventually. So you have here, so we have good classical models for this kind of two-level system, but they don't predict everything. So you have holes here that you need to develop the quantum theory for that, or at least quantum methods to analyze. And also we observe here decay of quantum correlations that are faster than predicted. So we have this superradiance. As I mentioned, we have this collective state in the excited state, and this should lead to this superradiance. We measure the dependence of this decay with the number of atoms, and it's consistent with superradiance yet. But also, we were able to measure, I mean, for many time scales, here is like 5 orders of magnitude time scales, these quantum correlations, and correlations in general in the system. So this actually, the correlations that we see in the quantum region are just related to this excited state process. For the long correlations, we are more in the classical regime. You see this purple curve here is the autocorrelation function, and the black points is just experimental data, and the green function is just an empirical expression that we developed. And so you see here at long times, the cross correlation, the autocorrelation, they just merge. You see this, you have two plateaus here. We understand that that's coming from two different gratings, so we have some scattering that comes in the forward direction, but you can also have a first scattering in the backward direction, and this gives two very different decay times. These are these decay times here. So here's log scale. Okay, so if you put in the linear scale, this is the difference in decay times. So basically, this long decay times is a collective state that starts with a forward emission, and the other one is one that starts with a backward emission, basically. Okay. So let's pass through another process. So we are going to now to Raman scattering. So Raman scattering, we are going to have inelastic scattering. I mean, you excite the system with a particular frequency, and then you emit in a different frequency. Okay. So this is also a very common phenomenon. And actually, for Raman process, you have much stronger correlations, because for two-level systems, you always have a competition between the emitted photons and the exciting fields. They are acting the same transition. But actually, for Raman, you separate the two. and this gets much stronger. So originally, this process was proposed in 2001. It's called, in the context of the DLCZ protocol, I'll come back to that later. And it was implemented the first time by Jeff Kimball's group at Caltech. So I started working this problem there in Caltech, but a bit later in 2004. And the group there in Caltech really put forward this problem in the beginning. But this was a very important paper, okay? Not only for quantum information, but also conceptually, because for these collective states, we know them since the 50s with Dick's work on superradiance. But the problem is that what we are going to observe from that. And even the first experimental verifications of superradiance, the groups that were verified say, oh, but we have alternative explanations, and we have alternative explanations. So there are many alternative explanations for the observation of superradiance. But this is the first work that say, okay, now let's use these collective states to store quantum information in the ensembles, and let's use it as the basic of a quantum communication protocol. So, and then you give really a concrete application for these collective states, and you also, you end up making it more concrete in this concept. Okay, so, but for these Raman transitions, now we have we can understand, now we have a good memory, so we can actually act first with an exciting field and then just wait for the spontaneous emission in a particular direction, okay? So we don't excite at the same time with the two fields. We are still going to use a four-wave mixing configuration to move back in time. And we can understand well this problem, generate a state like this, in which you have like a large probability of not generating any photon in field one and not transmit any atom to this other state here in your atomic system. So here in this configuration, you start with pumping everybody to a particular ground state. And then we calculate the probability to come to the other state. And then once you emit a photon, you transmit one atom to this other state, and so on. So actually you have a probability of excitation of these different states, of this cascade of states. So you have a probability of not doing anything, but you have a probability of generating, for example, this state here, which is a Dick state, in which you have one atom here in S, but you don't know which atom, so you have to symmetrize, symmetrize this probability between the atoms. And you can have two excitations also symmetrized here. And in the end, it's important to, oops. So what you have here is that if you put a detector here, so you do a conditional measurement, and then you eliminate the vacuum component here, and you end up with a single excitation stored in your atomic system. This happens exactly in the two-level system as well, okay? So you end up with this state there once you detect the first photon. But the problem in the two-level system is that after that, when you try to read out, you generate other states. But here, in the Raman transitions, I can excite in this other transition here, so I can read just this. So I can really select the collective state and act only on that during the extraction process. But this is exactly a more direct example of a conditional measurement in the reservoir. So as I mentioned before, you have this entangled state between a photon and now a collective excitation. Once you measure something in the photonic, in the light field, then you know something about the atomic state. In this case, you know that there is this state prepared. So then I mentioned earlier, we can read that. Okay, you come from a different field and come back to the initial state. And now, from this collective state, then you have superradiant emission. And so you have this Fock state that has no classical analog. You have this large suppression of any two components. So how large is this? For the G20, the best that I got was 0.7%, so 0.007. At the time, it was comparable with spontaneous parametric down conversion. 5 minutes, okay. So I'm going to just hurry up a little bit now. There's a lot to go, but it's fine. You see here, so it is an experiment that we did in Recife, where we just characterize the time of decay together with this G2 function. This is just to highlight a really quantum regime for superradiance, because now we have a single photon that's emitted collectively, okay? And just move forward. We can do a lot of things with that. We can do, for example, synchronizable single photon source. I mean, here are two sources that comes from different optical tables, and we show that we can do interference between these two photons, so they are really nice source of indistinguishable photons. This is an old paper I did during my time at Caltech, and this we did at Recife already. We use that as to generate two photons, so we can prepare with one photon, but we can also prepare with two, and then we can prepare a Fock state there, and then we can release it in a super radiant process, but now with two photons. So we have a lot of freedom to prepare these quantum states. And if you think that this is just for cold atoms, I always like this work here from another Brazilian group, where they measure exactly this kind of quantum correlations in G12. You see the G12 that they get is like 600, but they got that from water at room temperature. The thing is that you need to know where to look at. It's not the matter that the quantum correlations are not there. It's just that you really, normally you need to look for the right frequency. In the case of water, you need to look for the right sidebands to get this kind of correlation. And so, as I mentioned, this connects with some quantum information protocols, and these are also old papers from the time I was at Caltech, so we could use this process to actually generate entanglement between two different ensembles that were in different optical tables, or we could generate actually an entanglement among this group of four ensembles, which basically means that these four systems, they emit photons that are indistinguishable from each other. And this is quite important, the fact that you can really apply that for some particular problem. And this led to a generalization of a concept of quantum networks that was introduced there in Caltech, also for Kimball's work, and with Zoller and Siraki and Hideo Mabuchi. And this led to this concept of quantum internet in this work by Kimball. This work, he basically reviewed previous results of his group, but he coined this concept, which was quite interesting. And just now I'm flying through. It's just to explain that in Recife now we have a quantum network that we are developing, but it's really a small network, just a couple of kilometers. And then we are already passing some photon pairs on that. You see the G12 function over time, over distance in the fibers. So you see that for photon pairs from parametric Dow conversion, you have G12 in the scale of hundreds, but we can still preserve that in these length scales here. And we are developing an institute there. I'll pass quickly. It's just a combination of different fields, and all of these fields we have different projects in quantum technology. So now we put everything together, and then we have a project to just reform a floor in an old building of the university. Now it's empty, but it's going to be full soon. And we are going to have 3 labs there. One a photonic quantum computation lab, another quantum communication, which is a connection with the Recife's quantum network, and a third of the theoretical quantum computation lab. And now we have a more concrete idea about what we are going to have there for our photonic quantum computer. So we want to have magnetic optical trap here, a universal photonic processor, and a single photon detector. Our role is to build this magnetic optical trap. And the idea is that I talked about many different quantum states that you can generate from the atomic ensembles. You can generate entangled states, single photons, 2 photons, pure states. Now we want to have this machine so we can enter all these quantum states here and explore that for computation. The other parts we're going to buy from 2 different companies. And these are possible applications, both in quantum computation and quantum communication that we are looking for. And this is the actual map of our small quantum network. This dashed line here is the connection to this institute that we are setting up. And then we have this, we're going to have this quantum processor here. So basically we have this small network at 800 nanometers, actually. We are not going to use telecom, connected with this processor here at 800 nanometers. So that's our goal, to have a small quantum internet there at Recife. And finally, this is just the team, present day of the team. So I described many works. So the team that did this work is much larger than this, but this is the present day team that did some of these works, and this is the funding that I have to acknowledge as well. So thank you all.